evening, everybody. I'm actually very happy to be here today. It's just a wonderful place to give a lecture about the Milky Way. We're like in paradise here. I'm also very grateful for you, for your patience and perseverance, because this lecture has been canceled twice, and we're now here in really special circumstances, so thank you for being here. What I want to talk about today is how do we do archaeology with stars? And by doing archaeology with stars, what can we tell about how the Milky Way was actually formed? So what I want to start with is pausing at this, which is one of my favorite photographs in astronomy, if you wish. What this picture shows is it's taken on the top of a mountain in Chile. And what you see here is the splendor of the Milky Way on the sky, the beauty of the skies, right? And what I like about this picture is the contrast with this, little dome on the top of a mountain where an astronomer, maybe somebody like myself, is working to try to understand a little bit more about how the universe works. And what I find fascinating about this picture is this contrast between the vastness and beauty of the heaven and the small person here in the telescope, that despite this contrast in size, nonetheless, this person is trying to really understand how the galaxy, how the universe has formed and has evolved. And I find that one of the most fascinating aspects of astronomy. It's the large scale makes you feel small, but the fact that we have the ability to understand how things work by using the laws of nature that work on the Earth, to understand how something so vast like the Milky Way has formed, I find that actually amazing. So this picture was taken in Chile, but you can see the Milky Way from many different places on Earth. So what we're seeing here is a picture taken on the left from Tenerife, from the Canary Islands. You can see very clearly the Milky Way as the band of stars, whitish band of stars on the sky. You can see very clearly the Milky Way from a satellite. That's the top picture. You can see it also in Argentina rather well. That's where I come from, so I thought I had to put a picture of Argentina there. And yes, you can also sort of see it from the Netherlands, right? If you're lucky with the weather, and if you're in a really dark spot, then you can actually see a sort of whitish band of stars, whitish light. That's the Milky Way. So particularly if you go to the northern part of the Netherlands, close to where I live in Lauwersoog, there's a dark sky park being built with a telescope there. And you can actually, if you feel like traveling 200 kilometers, you can really see the sky rather nicely from there. If you're lucky with the weather, of course. Okay, so the Milky Way, as you know, receives its name from the band of light that we see on the white band of light that we see on the sky. And this white band is not just, it's really just stars, lots and lots of stars. And these stars are so far away that you can't really see the individual stars with your eye, and all of the light comes together and produces this one white band on the sky. What you also see on a picture like this is these dark areas, dark regions. These are regions where new stars are forming. So we see in the Milky Way, particularly in the disk of the Milky Way, we see a lot of star formation happening. Stars like suns, like the sun, are forming as we speak in many, many of these regions that are full of dust and gas. And as stars form, also planets form. surrounding the stars. And our estimate is at the moment that at least 50% of the stars have a planet around them. Maybe all of them. We just don't know yet. So the Milky Way is really a conglomerate of stars, planets, gas, dust, and dark matter. I'm not going to talk about dark matter, but you can ask me later if you're interested. And it forms our galaxy. It has this conglomerate has a very special geometry. It's like a flattened disk, like a pancake, and we're basically living in that pancake. And so when you project that on the sky, you see this whitish, this band of stars on the sky. So if you were able to travel outside of the Milky Way and look at the Milky Way from the top, then it would look like something like this picture, right? With lots of, say, spiral arms, as you can see here, where new stars are being born, a central region which is very bright, which you can also see around the Milky Way, in the Milky Way itself. But from the edge, it looks like this other galaxy, right? And we are sitting inside, and so we see this kind of edge. So about 2/3 of galaxies in the universe are disks, like the Milky Way. And in fact, the Milky Way is not really that special. It's actually rather typical in terms of how bright it is, in terms of its size, and then almost, say, 2/3, 66% of the galaxies in the universe are disks. So nothing special about it. So being so typical, that actually means that you can use it to understand how other galaxies have formed as a prototype, right? So if you have understood how our own galaxy formed, then you can extrapolate, or you can kind of use your understanding for trying to figure out how other galaxies formed. And so we can use it for that. We can also use it, for example, to understand what physical processes are important in, say, the evolution of the universe, in the buildup of galaxies. And we can also use it to understand what the universe is made of, right? Because there's no reason that the region around us is any different from any other region in the universe, right? So the types of matter that we find in our galaxy, the zero assumption is that it should be similar to the type of matter you find elsewhere, and this is indeed what we're finding. It's like you should think, or at least the way I think about our galaxies, it's like this little island, or if you wish, in the past we used to call galaxies island universes. So it's like your own spaceship, if you will, a very large spaceship. You know your own spaceship rather well, because you can see the individual stars, you can measure the properties, you can see how they're moving through space, like you know your city very well, right? And then if you want to go and explore another city, what you will use is the information that you already know about your city to try to find your way in other cities. So it's a basic idea in the kind of research that we do. But really, I think, to me at least, the reason I'm so interested in understanding the Milky Way is that actually the Milky Way is our own galaxy, right? And so it is, to me, our home in the universe. And if you're interested in understanding your own origin, then you're also interested in understanding how the Milky Way formed. So in terms of origins, then we would really like to know, what is the history of our home in the universe? So what do we know? So we have a theory, we have a model of how galaxies formed, and this is shown in this numerical simulation of the formation. At the end of the day, you'll see a galaxy formed. So what we're seeing is the evolution of structure in the universe from very early times to the present day. And the first thing you notice is lots of small galaxies that are forming. These are the red knots. They are surrounded by gas. And they're coming together because they are being pulled by the mass they have. They're being pulled together. This gravitational force is attracting all of these small galaxies to produce a larger galaxy, in this case, a galaxy that has a disk in it, right? It was also rather flattened. You saw a lot of merging activity, so lots of galaxies coming together very early on, but at late times, we're now coming closer to the present day, you don't see so many mergers going on. So at late times, the process of the formation of a galaxy is much more quiescent. And by the end of the day, from that, say, universe that was almost homogeneous at the beginning with very little structure, you can form galaxies like the Milky Way. So that's the basic idea that we have of how galaxies form. This is how we think, say, the universe around us looks like, or at least this is our model for the universe around us. Of course, this is a model, so the issue is, does it really work? Is this really the way that galaxies form? So if I take you through the history of time, so I'm starting here at the Big Bang, slightly earlier than where that simulation started, and I'm finishing at the present day with a satellite observing the universe, right? And so what we had initially is the Big Bang, so the universe starts small and very hot, it expands, and it cools down. And at some point, it's so cold that the first galaxies, the first stars can form. And in fact, we are at the moment observing not just the first stars, but we've observed also some of the very first galaxies to form. Now, as you can imagine, these galaxies are really very, very far away, right? So remember that because of the constancy of the speed of light, if we observe something that's really, really far, we're basically going back in time, right? So if we look at the sun now, we would see the sun the way it was 8 minutes ago. Now, if you put something slightly farther away, you can go back a year, a century, thousands of years, billions of years, right? And so the galaxy that you see here is something like 12 billion years ago. But we're seeing it today. So we're really going back a really long time. Now, because we're going so far back in time, there's not so much detail. You can't see the individual stars. You can't see spiral arms. All you see is a blob. But the galaxy is there. So that tells you a lot. It tells you there were galaxies forming at that time. Now, if we come closer by, then we actually see galaxies interacting, as shown here. So we can see the full population of galaxies developing, and we do see interactions like we saw in the movies. We see mergers taking place. If we come a little closer, then actually we come to our own home. We come to the Milky Way, right? And so the Milky Way, as you've seen in these pictures, has several components in it. It has the disk, as I was talking about, where most of the stars are. It has this central concentration, which is a bar, and it has a halo of stars around it. It turns out that some of the stars, most of the stars in this halo around the Milky Way, actually are, as far as we can tell, as old as the universe itself. Right? So that means that in this, say, time sequence, they formed around here. So these stars actually witnessed how the Milky Way was put together. They've been there since the very beginning. They saw what happened to the Milky Way. They saw it grow, right? And so what we want to do is to use those stars and the memory they have of the origin to actually learn about how the Milky Way formed. And that is basically what lies at the essence of doing galactic archaeology. It's using stars as fossils, as the reminders of the process of galaxy formation, to kind of rewind the movie back and figure out what happened in between. What's very special is, as I was saying, because we can observe stars and we can measure the properties, we cannot really do that for other galaxies, except for a few that are very nearby. So that is a very special way of trying to understand how galaxies in general formed. Now, let me see. So stars are not only distributed in different components that have, for example, different ages, like the halo was really, really old, but the stars are also moving differently in the different components. So in the disk of our galaxy, as you saw in the movie, stars tend to move on circular trajectories around the galactic center, whereas the older stars tend to move much more randomly around the center of the galaxy, right? They have more random motions. And that's also one way of distinguishing these different types of populations. Okay, so far, or until recently, this was our knowledge of the galaxy. We had made pictures. We know the structure of the galaxy in the sense of it being a disk. We know it has this central component. But really, in terms of the motions of the stars, we were restricted to the nearest bunch of stars to us. So if the sun were located here in the disk of the galaxy, we only really knew our immediate neighborhood. So if you imagine, the galaxy, if you draw it to scale, the galaxy is full of the Netherlands and the sun is in Amsterdam, then you only know your region around Amsterdam. You don't know what happens in Groningen, for example, right? And you don't know much about what happens in the halo, because most of the halo is outside of the disk, right? So you know very little about what happened a really long time ago from those old stars. And so what happened is, because we really wanted to understand our galaxy, what happened is we devised a space mission that's known as Gaia, which I hope some of you have heard from. And Gaia can actually measure how stars move through the galaxy. And the technology that Gaia uses is just so precise that it can actually measure the diameter of a human hair on the moon. Yeah, that's the kind of precision that Gaia can reach. And so with that precision, you can not only measure how stars are moving here, but you can measure how stars are moving really across the full galaxy. So Gaia has now collected a sample of stars that's 10,000 times larger than any other sample we've had so far, through a volume that's 100,000 times larger, with a precision that is 100 times better. And that is really leading to a revolution in the field. So Gaia was launched in 2013. It's a European Space Agency mission. And it was launched in December, I think, 17th of 2013. And I was then in Argentina. It was 6 a.m. for me, but I really wanted to see the mission go and, reach its destination, right? So you can see here Gaia, how it opened its sun shields and how it left the Earth. Gaia is spinning around its axis. It's at roughly 1.5 million kilometers from the Earth, and it orbits kind of behind the Earth around the sun at the same time. And as it spins on the sky, it actually measures the positions of the stars. It measures the positions of every object that basically falls in its field of view. Now, what happened after launched, Gaia started collecting data, and in April 2018, the second data release of Gaia was made public. And this data release had the measurements for 1.7 billion objects. And it's just an amazing data set that it's absolutely mind-blowing, and it's absolutely changing the way we think about the Milky Way. So one of the things that, you look at these numbers and you can't believe you have this kind of data on your desktop, right? So you can measure the positions of 1.7 billion objects on the sky. And for these objects, for a fair fraction of them, for 1.4 billion, you actually know how they are moving through space. That's just absolutely fantastic. For some of these objects, for also a fair fraction of those, we know how far they are. So we actually know the three-dimensional distribution of stars. We know where stars are located in space. And for a small fraction of those, only 7 million objects, we actually know how they are moving towards and away from us. So that is what you get from a spectrum, for example. We used to know rather well how stars were moving, say, towards and away from us, but we had no idea of how they were moving on the sky, and this is what the proper motions are giving us. And this is what Gaia is giving us. So with such a data set, there's a lot of different kind of science that you can do. You can look at, there's basically, for every astronomer, there's something you can do with Gaia. This is why I love the mission so far so much. So you can study solar system objects. You can look at stars near the sun and look at, for example, how stars are forming. You can try to measure the masses of exoplanets. You can learn about the structure of the galaxy. You learn about the distribution of dark matter around it in our galaxy, but also in nearby galaxies. And you can also observe distant galaxies and quasars, right? But really, the reason that Gaia was built was to answer this question. How did the Milky Way get to be this way? What kind of processes took place? And to answer that question, Gaia measured the motions of the stars. And this is real. This is based on the Gaia data. So what Gaia is showing us is that basically everything moves. Stars don't stay in their place, they just move around. And because they move around, if you think about it, if you see motion, there's a force that's driving that motion. So from the motions, you can actually learn about what kind of forces are driving those motions, for example. But also you can learn about the site of origin of the stars, right? If I see a bunch of stars moving, say, in some directions, I know they came from somewhere, and I can tell from where they came. And so all of that information can be used to understand how the galaxy formed. So this is what really galactic archaeology is about. And so what I showed you somewhere in the beginning is I showed you this movie of how we think a galaxy formed. And now these are snapshots from a different numerical simulation, but it's the same basic idea. So you start with small galaxies very early on, after the Big Bang. And these galaxies come together. They are attracted to each other because of their mass. The gravitational pull brings them together, and they merge. And in the process of merging, you get larger and larger galaxies, right? And so what happens is these galaxies are torn apart by tidal forces, and that gives rise to these kind of features or substructures here. If we look at the present day, then what we would see is this galaxy in the middle, and most of the stars actually in the disk were born in the disk itself. But these stars here in the halo, they come from these building blocks, right? So so then that means that I can use these stars, or in principle, I could use these stars to figure out how many mergers the galaxy experienced. So how many building blocks were there a long time ago? And what were the properties of the building blocks? And do these galaxies that were there very early on, do they have anything to do with the galaxies that we see around us today, or were they completely different? The stars, actually, and that's the nice thing about it, and that's why this is galactic archaeology, stars remember where they come from. They have memory of their origin. And the memory is in how they're distributed in space, it is in how they move, it is in their chemical composition, which tells you about the environment in which the stars formed, and it's also in the ages, which tells you when they were formed. So all of this information together you can use to actually reconstruct the history of formation of the galaxy. And so, for example, as I was saying, the stellar halo, the halo around the Milky Way, if it was built from, say, these different objects, and now I color-coded each star from each of the objects with a different color, then the stellar halo would look like something like this, right? So all the stars in magenta would come from the same object. In green, in yellow, there's blue, there's orange. So there's quite a few objects contributing to the halo, right? Now, the problem is I don't know which star. The stars don't come with flags that tell you, oh yeah, I was born somewhere else. You have to find the flags yourself. But this would be the basic idea. And so what you see is that if you look rather far from the center of the galaxy, so in the outskirts, you sort of see substructures, right? So you can sort of say, indeed, this galaxy has experienced several mergers, right? But if you look here in the inner regions, it all overlaps, and it's a mess. So how am I going to distinguish the different stars from the different objects that merged? And that's where motions are really critical. So what we see here is what happens to a small satellite when it's accreted by a galaxy like the Milky Way. And you can see it stretched and being torn apart by the Milky Way. And you can sort of see that if you wait long enough, then these red stars are really everywhere. So there's no information in the spatial distribution, but if you look at any given place, you actually see that they move coherently, right? So they're moving together through space. So in their motions, there's still memory of where they came from. In fact, if I take a still of that movie and I plot how the stars were moving, then what I would see is, for example, if the sun were here, I would see a bunch of stars moving in this direction and another bunch of stars moving in this direction. And these two streams of stars tell me, actually, that these stars were born in a different galaxy. So I had a couple of pictures that because I wanted to explain how we do find the merger history of the Milky Way. So I have a couple of plots to explain the basic idea. I hope this is clear. So we've seen this, right? So when a small satellite is accreted, you saw it gets fully disrupted. The stars are everywhere in space. But if you take a small portion, say you look at the vicinity of the sun, you take a small volume, then what you could see for this one satellite is you would see this bunch of stars going up and this other bunch of stars coming in this direction, right? If you now plot that in velocity space, right, so you would plot a velocity in this axis and one in that axis, then you would see both are moving upwards, so you'd see two clumps here, but one is moving to the right and another one is moving to the left, right? So then you see two clumps in this space. Now what happens actually, you can take it one step further, so that's one way of finding merger debris. We should just plot velocities against each other and see if we find clumps. Now there's an extra step that you can make, which is if you actually think about how these stars are moving through space, you can actually compute quantities like what is their energy or what is their angular momentum or the spin in their orbit, right? So how fast they are going around in their orbit. And it turns out that these quantities don't change with time. So if you think about a small galaxy, all the stars were together in the same place in the beginning. Then they had all similar angular momenta, right? If the angular momenta doesn't change, then at the end of the day, they will still be clumped in angular momentum. And this is what is shown here. So all of these stars that have very different kinematics, if you then choose a different space to plot them, like energy or angular momentum, you find them all fall in a single clump. Now, if we go back to our idea, right, we're thinking that the halo is formed from many different mergers, right? But we don't have the flags, we don't have the colors to tell us, okay, these are all the different mergers that took place. Then what you can do is you can plot their velocities, and then you would see for each one of the galaxies, you would see a clump in velocity, just like here. Or if you plot in energy and angular momentum, you would also see all the different clumps. And you can see now that even if you didn't have any colors, right, if I had made this picture black and white, you would still see structure in this space. You would still be able to distinguish features. Okay, so now we have a method, right? And we have the data. So then what happened? What did we find? Yes, so what I'm going to show you is a velocity diagram, and I just wanted to get this straight. So what I'm going to show you is how the stars in the vicinity of the sun are moving. And the stars can be moving, say, in the plane of the disk, like the majority of the stars in the disk, as I just showed you, they go around in circles, but they could also be moving with large velocities up and down, right, or radially. Okay, so the first plot we made of the velocities of the stars showed this. Okay, so this is it's gonna take a while, but this was amazing to see this, but I'm gonna tell you why. So what I'm plotting here is how stars are moving around in the plane, right? So how they move like this, the rotational motion. Now, we're looking near the sun, so most of the stars are in the disk, right? So most of the stars should be on this circular orbit around the sun. And indeed, this is this region here that's dark blue, and we don't plot every point because it would be totally black, right? So most of the stars are here. If you then move away more to random motions, which is your halo, then you begin to see two things. Okay, you see this kind of feature here that seems kind of the continuation of this structure here, right? And then you see this feature here, which is dominant. We don't see lots of small clumps. We see one big thing, which is this here. And the other thing that we see about this thing, which is really odd, is, so I put this line here. So the stars in the disk of our galaxy, they all go clockwise. Now it turns out that if you look at the halo stars, the majority are going in the opposite sense. That's weird. So it's like, you know, you have fish, and all the fish go into the same direction. They go stream upwards. But then you find this one fish that goes in the opposite sense. And it not only is weird because it goes in the opposite sense, but if you actually analyze the chemical composition of the fish, it turns out to be very different. And the chemical composition of the stars that are moving in the halo of our galaxy is very different from what we had expected. And it tells us immediately that the stars were not born in the galaxy, but were born somewhere else. This is like, it's quite funny because it's like, you know, you go to the UK and you're driving, right, as a continental European and you face a roundabout, and instead of going left like people from the UK would do, you go right. You can immediately tell that person is a continental European. This is the same. It's the same basic idea. You're going unexpectedly in a different direction. And it's not just a small fraction of the stars in the halo that are going in the opposite sense. It's the majority of the stars. The majority of the black points are really going in the wrong direction. So what does this mean? It means actually the galaxy experienced a major merger with one object. We can tell when this happened, and this movie shows you how that happened or how we think that happened. So there was this one large galaxy that came onto the Milky Way some 10 billion years ago. The Milky Way at the time had a disk. We can even tell that. And because this object was so large, as you can see in the simulation, it actually did quite a bit of damage to the Milky Way that led to the formation you saw in the movie. You had initially a thin disk. By the end of the day, what you have is a rather puffed up disk. So this event actually led not only to the formation of the halo, and basically all of the halo was born elsewhere, because it comes from stars born elsewhere in a different galaxy, but it also led to the formation of the thick disk. So another component of the Milky Way got formed because of this event. So it was really a milestone in the history of the galaxy. And so we had to give it a name, and we gave it the name Gaia-Enceladus. Why Enceladus? So we were looking for names, right? And so what we thought is, we want something big. So we looked at Greek mythology, because this is what you use to give names to astronomical objects. And it turns out that Enceladus is a giant in Greek mythology. It's actually the son of Gaia and the sky. It's actually, the myth says that it's buried under Mount Etna in Sicily, and it's responsible for seismic activity, right? So if you think about it, Gaia-Enceladus, the galaxy, is buried in the Milky Way. The remains are there in the Milky Way. It was also buried in the Gaia data. And it was also responsible for quite a bit of shaking at the time of the merger, right, producing the formation of the thick disk. Now, Enceladus was the biggest object that the Milky Way accreted or merged with in the last 10 billion years, but the Milky Way has accreted some other smaller objects, and we're currently in the process of trying to figure out what the characteristics of those objects are. So you've heard about my streams in the introduction. They're still there. When I found them, they had 13 stars only. Now they have 600 stars, so they're real. It wasn't a fluke in the data. We have Gaia-Enceladus, and we have a few other substructures. And we're in the process of trying to characterize these objects, because as I was saying, these stars were really born a long time ago. So they tell us about what were the conditions of the universe a really long time ago, with a lot of detail in a way that we could not have access to if we were to directly observe the distant universe. So it's very exciting times in the sense that we're really rewinding the history of the galaxy back. Now, what you can ask is, I told you about these huge numbers from Gaia, right? 1.7 billion objects. And now I talk about 600 stars in the Helmi streams. How do you go from a data set that's 1.7 billion to 600? How do you find these stars that you're so interested in? So what you need is really to have really good data mining tools, right? And so I had a postdoc in my group. He was amazing, and he developed this package called VAX that's publicly available and that can not only, say, be used to find stars from mergers, so by looking at energy and angular momentum, or plot the velocities of stars, or any flow and that you're interested in that is there in your data set. But it's also extremely efficient because it can be used to visualize 1 billion points in less than 1 second on a laptop. Right? So we're not talking about any machine that's very fancy. And so you can use, there are many data sets out there, so you just tried out whatever data set was there, and you can make plots of whether the drop-off locations of taxis in Manhattan, there are 1 billion points for such data sets. You can use it to study a simulation of the formation of structure in the universe, or you can use it to look at the light pollution in Europe, and again, you reach the conclusion, yeah, there's too much light in the Netherlands. But what's amazing, actually, and we found out that slightly later, is that actually this software was also being used to establish to what extent the night watch had to be restored. Right? And so you then see that software that was developed by this guy, Martin Bredos, to figure out how the Milky Way formed is now actually being used for so many other things, including, something like the restoration of the Nachtwacht. So I find that very, very nice. So Martin wasn't alone. There was a large group of people that throughout the years contributed with their knowledge and their enthusiasm to study to prepare for the analysis of the Gaia dataset and to make the discoveries we've made. So on the left-hand side, you see my group throughout the years. And on the right-hand side, you see the people that have worked for the Gaia mission in the sense of, getting the data the data is downloaded from the satellite to disk, but then you have to actually analyze the measurements to produce a catalog that can then be used for science. And so there are 500 people in this enterprise spread all over Europe that actually made it possible and made possible our discoveries. So what comes next? Okay, the second data release that I was referring to, that was done 2 years ago. That was in April 2018. And that was from only 2 years of data. So Gaia had been scanning the sky for 2 years only. But Gaia has been doing this for more than 5 years now. And what that means is that because you have many more measurements, your errors go down, so you can measure much more precisely. And so new data releases are coming out. The next one is DR3, already at the end of the year. And what's also nice about this data set is that, of future data releases, is that instead of just focusing on the stars for which we have the line of sight velocity, those were 7 million, now we'll have 150 million. So that allows us to go much farther out into the galaxy. So we can really ask how different regions of the galaxy were put together. The other thing that happens, so you'd think after this, oh, Gaia can do everything, right? But no. So one of the things that Gaia doesn't do is measure chemical composition of the stars. And so how do you do that? Well, what you do is if you have the light from a star, you have a prism, and that decomposes the light, you get a rainbow. And in that light, you'll see lines. And these lines are atoms that are present in the atmospheres of the stars, and these atoms correspond to different chemical elements in the atmosphere of the stars. And so you can use these atoms. These tell you how many atoms of different elements there are there. And so you can study, for example, different proportions of iron or carbon or oxygen or sodium, whatever you like. And so by these these atmospheres tell us about what were the conditions at the time the star was formed. And so stars that were born in the same place have the same chemical sequence. So it's like DNA, right? So it's like the chemical DNA. And so by looking at the chemical compositions of the stars, we're also hoping to go further back in time, as well as to get the velocities for even a larger number of objects. And for that, we're building instruments on telescopes. Again, some of these telescopes are in Chile. So basically, I think what I can say is that Gaia is actually helping us understand how nature put together the night sky, because the night sky is the galaxy. And so we're beginning to really understand why the sky looks the way it does. And I find that absolutely amazing. So what I would like to do now is to spend a couple of minutes on the sky, on something that is worrying me, which is if you now take a picture of the sky, a long exposure picture, so you stare at the sky for a long time, then you see these streaks. That's a picture of Neowise, which I guess some of you may have seen last summer, somebody that took a long exposure, so just sat on Neowise. And you see all of these streaks. The bottom two panels are pictures taken or images taken from telescopes by astronomers, right? So professional astronomers. What are these streaks? These are satellites. So SpaceX, Starlink, Amazon are launching lots of satellites. They've launched about 600 in the last couple of years. They will launch about 70,000 of these. And you can see what that does. And the sky is ours. The sky is is for humanity. The sky is of each one of us. And if we lose the sky, then what will future generations see? And we won't be able to answer the questions such as the questions I posed today, right? We will stop being able to address how the universe was put together, for example. So I think there is room for us to take ownership of the sky and say, you know, guys, this is all very nice, but if you put a little bit more money into your satellites, you can make them dark, right? And then they would not make these streaks. We wouldn't see them. And we would be able to carry out our astronomical observations. And future generations will not look to the sky, up to the sky, and will actually just see the beauty of it, right? So I think this is something to keep in mind. But let me actually finish on a virtual trip through the galaxy. I told you we now know where stars are located in the galaxy. And so let me take you through the vicinity of the sun and what would happen if you moved with a spacecraft towards the Hyades, which is a group of stars that you can actually identify rather easily on the sky. This is real data. This is where the stars are in space. This is our galaxy in 3D. Thank you very much.